Now we're going to shift gears completely and talk about ecology. Much like the lengthy discussion that we just had about American Indians and land policy and resources and so forth, um, this is going to be a really quick survey version of this topic. This is a topic that could easily be a semester-long course, and for my students who might be watching this lecture video, many of them are environmental studies majors or biology majors or wildlife and fisheries majors, and they will be going into greater detail, or already have, about at least some of the topics that I'm going to cover here. But I'm just, like I said, giving you the highlights in a way that can benefit people from all the different majors who might be taking this course. All right, well, to begin with, the very word ecology, let's define that. Noun, the branch of biology dealing with the relations and interactions between organisms and their environment, including other organisms, and it comes from the Greek word oikos, which means household. So ecology is the study of the household, in the sense that the earth, nature, any environment is, in a sense, like a house with a lot of different roommates in it. And this is the study of how those various roommates, some plant, some animal, and some mineral, get along together and make the household function. The word was coined by this guy, Ernst Haeckel, a German physician and biologist who was a friend and supporter of Charles Darwin. And he coined the word in 1866 in his book General Morphology, except he wrote it in German, so it wasn't pronounced ecology, it was rather pronounced Erkologi. And in an 1869 lecture, he defined Erkologi, or ecology, as the study of the conditions for the struggle for existence, hearkening back to Charles Darwin, right? Survival of the fittest. So it's a study of the conditions within which that struggle takes place. He wrote a book in 1873 called The History of Creation. In 1879, he wrote a book called The Evolution of Man. He also wrote an important article, The Economy of Nature. So there you go, the guy who came up with the term ecology. Now, there are four basic approaches to ecology that we're going to talk about. We will discuss each of them in turn. Human ecology, organismic ecology, economic ecology, we won't talk too much about that one because it's sort of self-explanatory. And finally, my favorite, chaotic ecology. We're going to begin with this lady, Ellen Swallow Richards, who was a chemist, the first ever female to graduate from MIT, and then she became the first woman to be an instructor at MIT. And she is the one in 1892, 20 plus years after Haeckel introduced Erkologi, to introduce the word ecology to American audiences, at a member of the Boston Boot and Shoe Club, of all places. So she is one of the foremost early practitioners of human ecology. That is an ecology that views humans as part of nature, rather than the old Western view of humans being separate from and above nature. Humans are part of nature. Human ecology kind of focuses on the human aspect of it, humans' role within the ecological household, if you will. 1907, she wrote a book called Sanitation in Daily Life. She was an early preacher of the concept of fresh air and clean water being important. Fresh air and clean water that is not polluted by industrial pollutants. Air and water necessary for life. Now, that sounds pretty simple, kind of like a duh sort of thing. But remember what we talked about earlier. In cities in the 19th century, it was common for just raw sewage to be all over the place, for the rivers to be polluted by all kinds of things, the air polluted by soot. So this type of a campaign was extraordinarily important. She conducted the very first water quality survey, which resulted in the very first modern sewage treatment plant in Lowell, Massachusetts, which is kind of appropriate. The first city to have modern sewage treatment, the first city to clean up the water, is one of the early cities that really kind of personified the Industrial Revolution in America. The second approach we'll talk about, the organismic approach, was pioneered by Frederick Clements, who wrote a book called Plant Physiology and Ecology in 1907. So he basically focused on the plant part of the environment and believed that the plant community is like an organism. Remember that concept that we talked about before of cities being almost like organisms. He's looking at plant life as being sort of like one living organism, which you could argue was finally something that reached its apex with this guy, but I digress. Anyway, Clements talked about the concept of ecological succession, that is, stages of development within an environment. So any particular area, the plant life there is going to go through different stages, each one getting a little bit closer to the ultimate form of plant expression for that area until it finally reaches climax formation, which is the adult form, the pinnacle of this succession of advancements. And that climax formation might be different in different areas. In the Great Plains, the grasslands are the climax formation. Once you get there, that is perfectly adapted for the region. Other areas, it might be a forest or something else. So, for example, you might have in the beginning a shallow depression in the earth that collects water over time and becomes a pond. As time passes, that pond, with the plant life multiplying within it, can become a marsh, become swampy, can become soupy. And then after that, as that continues through the ages, it can go from being a marsh to being muck. So essentially, really thick mud. And from there, over time, that really thick mud sort of gains substance, gains form, and is able to sustain larger types of plant life, like trees, and over time, it becomes a forest, and it has then reached its climax formation. So then, the climate determines what kind of soil you're going to have. Again, back to our example of the Great Plains. And then the soil determines what kind of plants you're going to have. And the plants determine what kind of animals you're going to have. So there are two types of plant succession. We're still talking about the theories and ideas of Frederick Clements here. There is primary succession, which has no or few initial germules. Places like lakes and rocks and lava flows and dunes. And then you've got secondary succession, which has a lot of germules attached and results from some kind of disturbance to that primary succession. That disturbance might be natural, like a forest fire, or it might be a result of human activity, such as humans coming in and draining the swamp. Whatever the source is, it causes that plant succession to go in a different direction in its secondary mode. In 1939, in the book Ecology, Clements coined the term biome. So let's define that one. Biome, noun / ecology. A complex biotic community characterized by distinctive plant and animal species and maintained under the climatic conditions of the region, especially such a community that has developed to climax. So biomes are particularly areas that have reached climax. In those areas, plants are the mediator. They mediate between the habitat and the animals. They are a food source. They're a climate buffer. And if, for example, you read Donald Worster's Dust Bowl, one of the classics of environmental history that I assign frequently, then you'll know that it was the plant life on the Great Plains that really determined everything. And when that native plant life, those native grasses, were suppressed or replaced, bad things started to happen. Well, along those lines, talking about the Great Plains and the Dust Bowl, Clements had a lot to say about that while it was going on. In 1937, he wrote a book called Environment and Life on the Great Plains, in which he posited that the grassland is the climax formation of the Great Plains, and that since that is the climax formation, it is a biome, and human intrusion into that biome is disruptive, because you can't improve it. You can't improve it. It has reached its climax formation, the ideal situation for that environment. So you come in and tinker with it, you're only going to cause problems. Humans, he said, had defeated the eastern woodland biome, but they were defeated by the plains biome, which they did not understand. And things like monoculture farming, for example, just planting wheat or just planting corn, transformed the grasslands and helped to produce the Dust Bowl, although that really was only one of the many factors. All of them related, however, to all of them except for the arid weather, related to human misunderstanding of the environment around them. All right, next let's talk about Paul Sears, who during that same time period, during the Dust Bowl, wrote a book called Deserts on the March. He was claiming that the Great Plains were being transformed into a desert, and he was not the first person to suggest that. A half a century earlier, people we've talked about had been suggesting that. But he said that the government needed to take action, and it needed to frame their land use policy on ecology, specifically climax theory, that if the government took the scientific approach, the ideas of Frederick Clements, that they could prevent this desertification of the plains. Now, a couple of other important works that came later in the 1940s were books like The Principles of Animal Ecology by Allie Emerson et al. There's actually several authors involved there. in which they were proposing the idea that lessons from the natural world could be used to cure social ills. Again, not the first time someone had said that. Back in the late 19th century, some people, in a very misguided attempt to frame sociological issues around Darwin's theories, came up with social Darwinism. Not the right kind of lesson to learn. However, in this case, the idea was that looking at how biomes work, looking at how different species interact in a beneficial way to one another is a good thing to apply to human life. Also, someone we've talked about already, Aldo Leopold, 1948, The Land Ethic, talked about two different moral approaches. Whoops, I spelled that approaches. We're talking approaches here. The A-B cleavage. So two different approaches, A and B. A is a homocentric approach. Nature's there for humans to use. Well, this goes back to our very earliest lectures, right? This is that traditional Judeo-Christian Western civilization view. B, ecologically centered. Nature as a biotic pyramid. Now, we're going to look at a biotic pyramid and what that means. But if you will recall, when we talked about Leopold before, I stressed that essentially he was stepping outside the Judeo-Christian Western worldview and was really using the worldview, whether he knew it or not, and I'm sure he was at least somewhat aware of it, of Native Americans. All right, well, pyramids are always fun. Let's look at one, the Eltonian Pyramid, named for its creator, Charles Elton, who was an English zoologist. So his theory was, his approach, his contribution, in order to be sustainable, each level in this pyramid has to be smaller than the one below it, right? Because if you've got the base of a pyramid that is one size, and then you've got the next level that is twice as big as the base, and that continues, you're going to have a pyramid that topples over. So here is his ecological pyramid. At the bottom, you have the producers, the plants. Then above the plants, you have primary consumers, the herbivores. Above them, you have the secondary consumers, the predators. And then at the apex, at the top, you have the tertiary consumers, humans. The apex consumers, there at the top of the pyramid. So let's go back now and look at this and think about it. Bottom level, the producers, that's plants. So you got plants in this area, and then you've got, let's say, deer, herbivores. There have to be fewer deer than there are plants, so far as the amount of plants it takes to sustain a deer. So you've got to have fewer deer than you've got plants. Otherwise, it's going to get out of whack. If you've got too many deer and not enough plants, you're going to have starving deer, and it's all going to fall apart. The level above them, the secondary consumers, let's say wolves. You have to have fewer wolves than there are deer or elk or whatever. Same reason, right? If you got too many wolves, then they're going to run out of things to eat. And then humans up there at the top have to be situated accordingly. So this is demonstrating what is called the trophic dynamic. Trophic, a word meaning pertaining to nutrition, also called sometimes the food chain. Now, here's why you have to have each level smaller than the one below it. Each time there's an act of consumption, energy is transferred. The producers have energy, energy that is created through photosynthesis from sunlight and so forth. And when the herbivores eat that, then they get part of that energy. Then when the wolves eat the deer, they get part of that energy, and it gets passed along, the energy that originated with the plants. However, with each act of consumption, some of that energy is lost, always. That's why each level has to be smaller than the one below it. And this is really the second rule of thermodynamics. Quote, in all energy exchanges, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. So unless you're introducing new energy, if you're dealing with the same energy that you had to start with, the energy, the potential energy will always be less than its initial energy. Another similar, somewhat related concept is the concept of entropy. The idea that with each transfer of energy, some of that energy dissipates. So, new energy has to be introduced for it to keep going. Now, the trophic dynamic we just talked about, right? It said unless new energy is introduced, each act of consumption is going to be less than the initial. So if the second act is less, the third act is less than that, fourth act is less than that, no energy gets introduced, you're going to have finally nothingness. So new energy has to be introduced or everything will wind down. I have a couple of pictures to demonstrate how this works, although I can never be sure anymore how many of my students actually know how an old-fashioned wristwatch works that doesn't have batteries. You used to have to wind the thing, that little dial there on the right side of the watch. Every night you wind it up, and the motion of that winding that turns the internal gears is energy. And by winding it, you reintroduce more energy. So the thing keeps working and keeping accurate time for the next 24 hours. Or your car, the internal combustion engine. Every time you step on the gas and you have that consumption of energy, it propels your car forward. But if you keep doing that, eventually you run out of gas. So the only way that you can keep going is to fuel up, introduce new energy. So all of that comes under the umbrella of organismic ecology. Now, economic ecology, like I said, is pretty self-explanatory. It is about the economy of the environment and how it can be used to benefit humans. So I'll just kind of move from that one to the one I like talking about the most, the chaotic approach. Chaos theory. A chaos theory, which I think was first introduced in the 1970s and started to take hold in the 1980s, is an interdisciplinary approach that works in all number of different scientific and mathematical endeavors. The first time I was introduced to it was in the late 1980s when I read the novel Jurassic Park by Michael Crichton. If you remember the character who was later played by Jeff Goldblum in the movie, mathematician, was always talking about chaos theory. The idea that dynamic systems in motion, are extremely sensitive to random elements, such as what is called the butterfly effect. Some of you are probably familiar with that. The idea that a butterfly's wings flapping on the other side of the world can have the cumulative effect of adding just the right amount of extra wind energy to a developing weather system that could end up contributing to being sort of like the last straw that broke the camel's back of starting a hurricane. So the idea that little things creep in, and if you think about that in context of Jurassic Park, I'm assuming most of you are familiar with that franchise. Basic storyline is that this scientist wants to open an amusement park with cloned dinosaurs, and the mathematician character is like, hey, you know what? That's going to go wrong. Something's going to go wrong, no matter how safe you say it is. By the way, written by Michael Crichton, who also wrote about 10, 15 years earlier, Westworld, which some of you may be familiar with now because of the HBO series. But the plot of Westworld, if you're not familiar, was that this scientist designs a bunch of robots and opens an amusement park where people interact with the robots, pretending that they're gunfighters or samurai or whatever. And in that case, the intrepid hero says, "Hey, you know what? This is not going to work. Something will go wrong." That's basically what chaos theory is. Something's going to go wrong because there's no way. There is absolutely no way that in a dynamic system you could think of every conceivable variable and account for it and counter it. It's impossible. And you'll notice I have a picture of Jeff Daniels in the Civil War. This is from the movie Gettysburg. That came out almost 30 years ago. It was a big ensemble cast, although Jeff Daniels was a standout, playing the role of Lieutenant Colonel Joshua Chamberlain. So I'm going to tell you about Lieutenant Colonel Joshua Chamberlain, and then you'll see what this has to do with chaos theory. Joshua Chamberlain was the lieutenant colonel of this regiment from Maine that was part of the Union Army forces in the Battle of Gettysburg in Pennsylvania. His regiment was given the task of holding one of the several hills around town, the hill called Little Round Top. It was the hill kind of on the very end. If the Confederates got up that hill, they could then sweep around and flank the Union forces and hit them from the side and from behind and overrun them. So it was imperative that Union forces hold this hill. So they're up there on top of the hill, and they've run out of ammunition, which is a bad thing. And here is where a bizarre, unlikely chain of coincidences comes in. For one thing, Joshua Chamberlain wasn't supposed to be in command of the regiment. He wasn't the colonel, he was the lieutenant colonel. But the colonel got killed a few days before, so now he's in charge. For another thing, Joshua Chamberlain, in his civilian life before the war, just happened to be a college professor at Bowdoin University, a historian whose realm of expertise was classical history, Greece and Rome. Because he was so intimately familiar with Greece and Rome, he knew how to form a phalanx, which is where the soldiers would all link their shields together and have their spears poking out, and they'd be tightly compressed, kind of like into a triangle shape, like a wedge, and then they would be virtually unstoppable. So he formed his men into a phalanx. Even though they were out of ammunition, they had their bayonets in the place of spears, and this tightly formed phalanx came charging down the hill into the charging Confederates and bowled them over and scattered them and held the hill and won the day. It just so happens that most historians, I think, would agree that the Battle of Gettysburg was the turning point of the Civil War, after which it became inevitable that the North was going to win, or almost surely going to win. It had not been inevitable before that. It had been very much up in the air. Because the Union won the Civil War, slavery ended, and the country remained one country, was reunified. All that because there just happened to be a guy who just happened to be in charge when he wasn't supposed to be, that just happened to know exactly the right thing to do in the hopeless situation he was confronted with. And if you were to run computer simulations of that battle without knowing the personnel, You could run 10,000, 100,000 simulations, and you might not get that result because that was a bizarre X factor that could not be predicted and could not be accounted for. That's chaos. So chaos theory, you cannot preserve something that is constantly changing. Remember, we're talking about dynamic systems. And you cannot predict, order, or manage natural systems with absolute flawless precision. There are too many variables, which is why you can't completely accurately predict the weather. You can have a pretty good idea. You can come close. You can have a pretty good track record, but you can't completely, with no doubt whatsoever, say what's going to happen. Or not just general weather, but weather phenomenon like tornadoes and floods and so forth, because there are too many variables. Some of them tiny, like the wings of a butterfly, but those tiny effects can make an important difference in how things turn out. Perfect balance cannot be maintained. Okay, well, some other ways of looking at chaos include this concept called nature's pulsing paradigm, which was introduced in 1995 by the Odoms. The Odoms being brothers Howard and Eugene Odom, and Eugene's son William. So 3 Odoms. Yes, the Odoms family. I don't know if they were creepy or if they were kooky, but they knew their ecology. So this pulsing paradigm they came up with particularly deals with areas that are on the edge of chaos, like marshes, swamps, seasonally flooded areas. And their argument was that nature is not a balanced ecosystem at all. It pulses. It has oscillations. It's on the very edge of chaos, then it pulls back, then it's on the edge of chaos, then it pulls back. Each of these pulses causes it to expand and contract, if you will. So there are internal pulses, like storms, could be caused by dams breaking and so forth, or natural dissipation. External and internal systems kind of work together to create this pulse. Then you've got complexity theory, which is a part of this pulsing paradigm, that those complex systems exist on the very edge between order and chaos. They cannot be completely ordered. And they're never completely chaotic. They are both ordered and chaotic at once. There are multiple parts, and those parts are sensitive to initial conditions. And this is things like ant colonies. Ant colonies are huge, right? And so anything that happens outside of the normal or the expected is going to cause a pulse within that system. Same thing with the human nervous system. I would say probably from the experience of all the cars that have died on me, transmissions. Human economies. Oh, the economy is so sensitive to things that you can never completely predict. So, to summarize, you've got 4 types of ecology. Human ecology, in which humans are a part of nature. It studies how the environment affects and impacts humans. That was kind of like the first step, right? Before people could get around to broader thinking about ecosystems, first they had to, look at humanity as part of the ecosystem and how it affects people before they were able to move on to other things. So that's human ecology. Organismic ecology, also called scientific ecology. nature is studied separately from humans. In this scenario, humans are the intruders. And in this scenario, balance is possible, mostly if you keep the humans under control. Economic ecology, humans are above nature, and it's a study of how the environment can benefit humans. And chaotic ecology, nature is unpredictable. Nature's not necessarily kind. Sometimes nature is the aggressor, as opposed to the organismic approach, right, where nature is just nature and people come along and screw it up. Sometimes nature is the agent of chaos or destruction. And there is no way to ever achieve perfect balance. All right, so this was a lot of stuff. These were a lot of terms. This was a lot to take in. I've been talking for 35 minutes. Normally, if we were in person in class, classes, well, they used to be 55 minutes. Now maybe they're back down to 50. But regardless, we would have reached this point at about minute 35, and then I would have told everybody to go home, because that's enough for one day, essentially. It's a lot to take in and a lot to think about. So, take a breather, and then when we pick back up, we're going to be talking about the transition from conservationism to environmentalism in the 20th century.